Proceed. Okay, so we're looking at definite integration.
Is that a different reaction? First you're going to make me move.
And let's just recap how integration all works. So, who was the person who developed the integral sign and the integration process? Who was it? Riemann. Riemann, maybe with 2 N's, I think. Okay. And what was his method?
Dividing the space into smaller parts.
Substitution.
Substitution? No. Dividing the space into?
Smaller parts.
Smaller parts, right. So he started off with left rectangles, like so. And then found a pretty good approximation, and he found that you could use smaller rectangles means more accurate answers, right? Then what did he do?
He kept the equation.
No, before that. Yeah, he moved towards the right rectangles. So if I was to do this with right rectangles, then that means the right corner is now the rectangle that we're going to use. Okay, like so. And he found an approximation as well, and then figured, well, I could get even more accurate if I took the average between the 2 answers and called that one the trapezoidal rule. Okay, so that was the average. And formula for the trapezoidal rule is?
Half
FA.
Fx and then plus 2
2F.
Oh, whoops.
Yeah, 2.
Plus
2, yep.
Plus 2 fx 3. Continue, and then the last term is not double. The last term is just fx
to the end.
To the n. Thank you, and just means the last term. That's right. And is that complete now? We need a h, right? Because h represented the height. And where's the h go? There? Or there. We could say there. Okay, it's not half, but h on 2. All right, so that's the trapezoidal rule, which gave us a fairly accurate answer. And I think when we've tested it, we came to 2 decimal places quite accurately. But to get it very accurate, basically, Riemann made each of these rectangles really, really small. Okay? And so this distance here, we could say is h. Okay? And as h approaches the value 0, we get a distance that we'll call delta x. Okay, a very infinitesimally small distance. And it's a width. So delta x is a width. And this distance from here to here, if we call this coordinate x1, then this coordinate here would be the function of x1, right? That's the y component. And so f of x1 or f of x2, f of x3, is that the length or the height? Is that the width or the height?
Height.
So f of x1 is a height. So what Riemann did was, okay, he wanted to take the sum of all of these tiny rectangles, and he needed a symbol for the sum of the width, which is delta x, times by all of these heights. right? And so basically he's just adding a whole bunch of rectangles that have these tiny, tiny, tiny widths. The sum of, well, you know, S was already used for something else. What did we use S for? Begins with D.
Oh,
Displacement. Okay. We've got sigma, which means the sum of
All.
right?
Yeah.
Sorry? Yeah? The sum of all. And then we've got lowercase sigma, which we use for standard deviation. So he came up with his own S. That just looks like that. The height is f of x. And the width, delta x. Okay, and we don't use the triangle so much. And it's perhaps because maybe it's just a technology thing where very hard to find triangles on our keyboard, and so we just use D for delta. Okay, I don't really know if that's the reason why, but maybe it is. And so that's how he came up with the area under curves. Comes up with that. Okay. Now, if he wanted the starting interval to be x1 and the final interval to be xn, he just placed them there and there. So let's say the starting interval is A, the finishing interval is B. A and B is what we call intervals. Okay, that's your lower bound, that's your upper bound. Right, so let's do a quick example. Let's say that we're going to find the area of a sine curve. Let's say that this function is sine x. Now, help me finish off this graph. What are the values for the x and y axis? Start with the y axis. What goes here and here?
1 and -1.
1, -1, and on the x axis?
Pi on 2 and 5.
Pi and 2 pi. Which means that we already know where the maximum and the minimum turning points are, right? Where are they?
Wait,
Where are we going to find the maximum? That's pi on 2.
Pi on 2.
This one's 3 pi on 2.
Yeah.
Okay. Good, just because we do a lot of derivatives, so it's good to know. So, if we wanted to find the area between the curve and the x-axis, we could use the Riemann sum integration from 0 through to pi on the function f of x with respect to x, and that represents this one here, true?
Yep.
And we could add that to this area, which is pi to 2 pi on the function f of x with respect to x. The function of x is sine x. What's the integration of sine x? Cosine x.
Negative cosine.
Negative cosine x. There we go. I really should use square brackets. I need to be, let's be proper.
How come it's plus instead of minus now, so?
Oh, I'm sorry. Yes, my pardon. No, it is plus. Okay. I haven't substituted the lower and the upper bound yet. So that's our next step, and you'll see where the minus comes in. So when we plug in pi into the function, we're going to subtract the lower bound.
Right.
Okay, so that is just this portion.
Yep.
and then we're adding two areas. So really, we're doing two integration questions. Okay, so then we have negative cosine 2 pi subtract cosine pi. Okay. Right, let's see what this comes up with. So what is cosine pi?
1.
-1.
Negative 1, good. So this is negative 1 plus cosine 0.
1.
Cosine 0 is 1, good. Then
He said none.
cosine 2 pi.
Wow.
1, so I've got negative 1 here. Double negative is a plus. What's cosine pi?
1.
Negative 1.
Negative 1. Okay. It's good we're doing this. Right, so I've got double negative, so I've got 2 here. And this is going to come out to be negative 1, take away 1 is negative 2. And so my area is 0.
Ooh.
And we're done. Does that look right? No, you're all going to be confused because how can an area, first of all, be 0 when I can see 2 shaded regions? What happened?
Summed area.
What he said.
The area below cancels.
Yeah, the area below, which is a negative area, cancelled out the positive area. And that's why we've got 2 and negative 2. So we have to use the absolute value. Ben Jared, very good. So if we take the absolute value there, and here, and here, and here, and here, and here, really we get 2 plus 2, which is 4 units squared. Now we're done. Thanks, Sonia. Can you?
Wait, what? Did you just separate them? Is that all you did, sir?